Finding the interval of convergence of a power series. Objectives. By the end of this lesson, you should be able to find the complete interval of convergence of a power series using the geometric series test, and find the complete interval of convergence of a power series using the ratio test, and then testing the endpoints for convergence. Steps for finding the interval of convergence of the power series from n equals 0 to infinity of c sub n times x minus a to the n. So if c sub n is constant, then we can apply the geometric series test to find the complete interval of convergence. But if c sub n is a function of n, we must apply the ratio test to find an incomplete interval of convergence at first. Now it's incomplete because we have to test the endpoints for convergence. Now that we have all the tests to determine whether a series converges or diverges, now we need to test each endpoint in the original power series to decide if the series converges. If so, include the endpoint, otherwise exclude it. Alright, in this example we want to find the interval of convergence for the sum of n equals 1 to infinity of pi times x minus 2 to the n. So this power series has a constant where the c sub n goes, so this means this is a geometric power series. So the nice thing about this is we know that a geometric series converges if the r value is strictly less than 1. So in other words, to find the interval of convergence, all we need to do is take the absolute value of r, in this case the absolute value of x minus 2, and solve for when this quantity is less than 1. So the absolute value of x minus 2 is less than 1 whenever negative 1 is less than x minus 2 is less than 1. So now we can just add 2 to all parts of this inequality. So I would get 1 is less than x is less than 3. And because this is geometric, I have found a complete interval of convergence here. From 1 to 3 is my interval of convergence. And no other work needs to be done. And that's because this was of the form a times r to the n. So in this case, my r value was x minus 2, and I could only use this because my a was a constant. So pi is not a function of n, pi is just a number. Alright, so now let's try to find the interval of convergence for the sum from n equals 1 to infinity of 2 to the n over n times 4x minus 8 to the n. So this one is not geometric, as my c sub n term in the power series is a function of n. So in this case, what I have to do is apply the ratio test, where I want to show that the limit as n approaches infinity of a sub n plus 1, so this is 2 to the n plus 1 over n plus 1 times 4x minus 8 to the n plus 1. So that this is a sub n plus 1 over a sub n, so instead of dividing, I'm going to multiply by the reciprocal. So what's going to happen is I'm going to get an n over 2 to the n, and in the denominator I'm going to have my 4x minus 8 to the n. So this is really over 1 here. So now what I want to do is force this quantity to be less than 1, because I know that the ratio test converges when this limit is less than 1. So now there's a kind of a bit of simplifying to do. So let's take a look at the 2n plus 1 and the 2n, or 2 to the n plus 1. So this is 2 to the n times 2 to the 1. So this 2 to the n and this 2 to the n will cancel, because all this is multiplication and division. So from the 2 to the n plus 1, 2 to the n, all I have left is the 2. So now let's compare the n and the n plus 1. So I'll have n over n plus 1. And then I'll have, well, I have 4x minus 8 to the n plus 1. And then on the bottom, I have 4x minus 8 to the n. So the 4x minus 8 to the n will cancel with 4x minus 8 to the n here. So all I'll have left is one copy on the top of 4x minus 8. So now I'm taking the limit as n approaches infinity of this quantity, and I want this to be less than 1. So as n approaches infinity, the only terms with the n in it is n over n plus 1. So as n approaches infinity, this quantity right here goes to 1. So when I've evaluated this limit, once I've had n approach infinity, so this limit's gone and this quantity's gone because this just became a 1. So here's what I have left, 2 on the inside, and I have 4x minus 8 on the inside has to be less than 1. So I have 8x minus 16 has to be less than 1. And I'm solving for the x values here. So let's make a little bit more space. So what I want is for negative 1 to be less than 8x minus 16 to be less than 1. So I'm solving this inequality for x. So I'm going to add 16 to both, or to all three parts. So if I add 16, and add 16, I'm going to get 15 is less than 8x is less than 17. And then divide everything by 8. So sorry I ran out of space here. We'll move it up over here. So 15 over 8 is less than x is less than 17 over 8. So my possibilities for an interval of convergence here are 15 over 8 to 17 over 8 with either parentheses or brackets around either side of these two numbers. So in other words, I can't just assume it's open parentheses or closed brackets or open close on either side. I have to check. So now what I have to do is take 15 over 8 and 17 over 8 and plug both of those quantities into this x and see whether or not that series converges or diverges. So I have the sum of n equals 1 to infinity of 2 to the n over n. And now let's plug in 15 over 8. So 4 times 15 over 8 minus 8 to the n. So what's going to happen here, this 4 will cancel and this will become a 2. Oh, this is ugly. So now we have, 15 over 2 minus 16 over 2, if I write common denominator. So this is negative 1 over 2 to the n. And this is 2 to the n over n. So let's see, what can I do here? Actually, this isn't too bad. So this is 2 to the n over n. This is negative 1 to the n over 2 to the n. So I'm distributing the exponent of n here. So the 2 to the n's actually cancel. So my series is the series negative 1 to the n over n from n equals 1 to infinity. This is an alternating series here because of the negative 1 to the n, and each of the terms are getting smaller. So I have 1, 1/2, 1/3, and the limit of the general term goes to 0. So by the alternating series test, this converges. So what does that mean? So what that means is that at 15 over 8, I'm going to include that number using closed brackets. And so now I have to do that exact same process with 17 over 8. So I have to plug 17 over 8 back in up here. So let's erase all this, and we start over again. So now I'm going to go ahead and plug in a 17 over 8 to this x. So 4 times 17 over 8. So the 4 will cancel, the 8 will become a 2. So I have 17 over 2 minus 16 over 2 to the n. So now this is going to be a positive 1/2 to the n. And then I have 2 to the n over n, and this is a series from n equals 1 to infinity. So now, again, this is going to be 2 to the n over n, 1 to the n over 2 to the n. So the 2 to the n's will cancel. 1 to the n is just 1. So I'm doing the series, the harmonic series of just 1 over n, which we know diverges because it's harmonic. So because this diverges, I would not include that endpoint on the original interval of convergence. So my interval of convergence is closed 15 over 8 to open 17 over 8. So clearly, way more work when the original power series is not geometric. So we have to do the ratio test, forced this limit to be less than 1 to get my endpoints of my interval of convergence, and then I had to test the endpoints by plugging each of them back into this x, because these are x values for the interval of convergence. So this is my final answer. Alright, in this example, find the interval of convergence for the sum of n equals 1 to infinity of negative 1 to the n times n over 4 to the n. So there's my c sub n, which is not a constant, so we're going to have to use the ratio test, times x plus 3 to the n. So let me go ahead and start over here and write kind of small because we know this is going to be a lot of work. The limit as n approaches infinity of the absolute value of negative 1 to the n plus 1 times n plus 1 over 4 to the n plus 1, and then we have our x plus 3 to the n plus 1 in the numerator. So this is going to be times the reciprocal of this, because it would be divided by this quantity. So times the reciprocal means the 4 to the n is on the top, and on the bottom is my negative 1 to the n, my n, and my x plus 3 to the n. And I need to force this to be less than 1. So let's try to do a lot of simplifying all in one step here. So first, my absolute value bars are going to get rid of these alternating parts. And what we're going to have left is the absolute value of my n plus 1 over my n, so those stay there. This 4 to the n plus 1 is 4 to the n times 4. That's the same thing. So the 4 to the n and that 4 to the n will cancel. So it's like I have a 1/4 here. And this x plus 3 to the n plus 1 and x plus 3 to the n, that's going to cancel, that's going to cancel, and I just have an x plus 3 in the numerator, and that has to be less than 1. So as n approaches infinity, this quantity is going to go to 1. So this is gone and that's gone. So what I have is 1/4 times x plus 3 in absolute value bars has to be less than 1. So I have negative 4, or negative 1 is less than 1/4 times x plus 3 is less than 1. So first we multiply everything by 4 to get rid of that 1/4. So negative 4 is less than x plus 3 is less than 4. Then we subtract 3 from everything. So negative 4 minus 3 is negative 7 is less than x is less than 1. So my interval is going to be negative 7 to 1, and we need to decide close brackets or open parentheses. So we take the negative 7 and we plug it back into this original x. So let's go ahead and do that scratch work over here off to the side. So what we're going to have is the sum of n equals 1 to infinity of negative 1 to the n times n over 4 to the n. And when I plug in negative 7 here, what's going to happen? I'm going to have negative 7 plus 3, so that's going to give me a negative 4 to the n. So let's do some rewriting here. This is going to be negative 1 to the n times n. Negative 4 to the n is negative 1 to the n times 4 to the n over 4 to the n. So in other words, the 4 to the n's are going to cancel out. I have negative 1 now to the 2n. So anytime I have a negative to an even power, because 2n is going to be even numbers, it's like I just have positive 1. So these two things are going to cancel out. So all I really have left is just n. So I'm trying to decide whether the sum of n equals 1 to infinity of n is going to converge or diverge. Well, by the nth term test, n is going to diverge, right? I'm adding 1 plus 2 plus 3 plus 4. So around negative 7, I'm going to have an open parentheses because my series diverges. So now when I plug in 1 into this term right here, what's going to happen? If I plug in 1, I'm going to get just 1 plus 3, so 4 to the n. So in other words, I have the sum of n equals 1 to infinity of negative 1 to the n times n over 4 to the n times 4 to the n. So my 4 to the n's are going to cancel, and now I have this alternating series here, the sum of n equals 1 to infinity of negative 1 to the n times n. Well, this too is going to diverge, right? So now I'm trying to take negative 1 plus 2 minus 3 plus 4, but that will diverge by the nth term test as well. So this is going to diverge. So I do not include either of my endpoints. So my interval of convergence is open from negative 7 to 1. Alright, final example, find the interval of convergence for the sum of n equals 0 to infinity of n factorial, so my c sub n is not constant, times 2x plus 1 to the n. So we'll need to use the ratio test, the limit as n approaches infinity, the absolute value of, so we're going to end up with an n plus 1 factorial times 2x plus 1 to the n plus 1 over, so since we're not dealing with a rational function, I'll just put it directly over a sub n, which is n factorial, times 2x plus 1 to the n, and I need this to be less than 1. So let's see, this 2x plus 1 to the n is going to cancel with this here, and I'll just have one copy of 2x plus 1. And my factorial is going to cancel, and I will just have an n plus 1 on top. So what I have is n plus 1 times 2x plus 1. And I need this to be less than 1 as n approaches infinity. Alright, so here, as n approaches infinity, well, n plus 1 is going to go to infinity. So this quantity here is going to get really, really big. So if I take a really, really big number, and I'm multiplying it by whatever this is, this 2x plus 1, this is going to be a really big quantity. So in other words, can I ever plug in any x value here that will make this quantity less than 1? The answer is no. So here, there's not going to be any x value that satisfies this inequality. So there's nothing for x that I can plug in that will make this entire thing be less than 1. Because if I'm multiplying this by bigger and bigger numbers, this is still going to end up being a number that is greater than 1. So there's no x values that will make this work. So that means that my interval of convergence is just the center of this power series. So the center of this power series is actually going to be, if I take 2x plus 1 and set it equal to 0, then I'm going to get x equals negative 1/2. So this is going to converge at its center, which is 1/2. So my interval of convergence is simply the one number, negative 1/2. It's just the center here. So this is that worst possible scenario where my power series only converges at its center.